Okay, I guess let's get started. So today it's my great pleasure to introduce Ewin Tang as our speaker for this Aqua seminar. Ewin is currently at the University of Washington, and she's already well known for breakthroughs in quantum computing theory. If you have any questions during the talk, feel free to post on chat, and I'll keep an eye on that. Ewin, is it okay if we interrupt you with questions sometimes?
Oh yeah, that's fine.
Okay, great. Then please go ahead and get started.
Okay, thanks for having me. So I'm going to be talking about quantum linear algebra for machine learning. I'm going to, talk about, just try to give a introduction that might hopefully be like broadly accessible, but I don't know if I've achieved that. So feel free to ask questions or if you like. So the basic motivation behind studying quantum linear algebra, or like in particular quantum machine learning. So the sort of, the aspect I'll be looking at will be this following motivational question of whether a best of all possible worlds quantum computer can speed up machine learning tasks. And so since you're assuming like the best possible quantum computer, you might wonder like, why would you do this? Like we're not probably in the best possible world. But there are a few reasons to think about this. First of all, as a theorist, it's nice to think about these kinds of algorithms because they're usually quite elegant and quite natural. So, I mean, that's pleasant for me. The second thing is that if you can prove that certain things aren't possible for like a best of all possible worlds quantum computer, then this will have like broad implications on even the quantum computers that we do construct in reality. And third, I think maybe it's important to be able to understand the claims that can be made about quantum computers. You know, there's a lot of funding being put into like what quantum algorithms quantum computers can do. So this is sort of like the very edge of what people can say is possible. So in some sense, I feel like my work is a little bit of like a fact checker sometimes. That's like how I like to think about it sometimes. Okay, but we'll begin with discussing what exactly quantum linear algebra is. So this is going to be based off of some a nice framework in this paper for quantum singular value transformation. Now, this is going to assume slightly more than a typical quantum linear algebra. Like, it unifies all of like quantum linear algebra, but it does so at some cost of like, you need to assume slightly more, but it's not a big deal since we're assuming a really good quantum computer. So yeah, just I'll elide some of the actual implementation details here. And actually for the whole talk, I'm going to be sort of ignoring details of like actual complexities and mostly talk about like what's possible. Okay, so the fundamental notion in this quantum linear algebra framework is that of the block encoding. So so block encodings are ways to implement matrices. So if I have a matrix A, I say I have a block encoding of it. If I can efficiently apply a unitary that sort of has A inside of it. So here, it doesn't really matter where it is, but here I've just put it in the top left corner. So here U is U has A over alpha, so scaled down by alpha in the top left corner. And this corresponds to this corresponds to A being the thing that you get when you sort of I guess, yeah, this encodes looking at the top left corner. So you sort of if you wanted to get A, you would sort of add all these auxiliary qubits, then apply U, and then measure and post-select on them being 0. But it's not super important. And here, notice that when I select alpha when I describe this alpha block encoding, this A over alpha needs to be spectral norm at most 1. This is just so if it was larger, then it actually couldn't be encoded into a unitary, since a unitary has spectral norm at most 1. And so this means that alpha has to be at least the spectral norm of alpha. It could be larger. I guess operator norm, I say here. And the sort of way I like to think about it is that alpha is sort of some upper bound that we know of for alpha, for A, for the spectral norm of A, sort of a priori. And this alpha is going to be like the parameter that basically determines some of the details of like complexities later on. Okay, so the reason why this is a quantum linear algebra notion is that you can, if you have a block encoding of A, you can basically apply it to vectors. So we can encode a vector into the magnitudes of a quantum state in the following manner, just by putting the entries as the various amplitudes. And here, this spectral norm is just for normalization. And if we can do this, if we can make this vector V, we can do this encoding, then again, as I discussed before, we can append a bunch of qubits, apply U, and then post-select on the first A qubits being 0. And when you do that, you'll be able to see the vector corresponding to AV with probability proportional to this. So right. And one thing to note here is that because you only see it with a particular probability, this means that sort of if you want to use your block encoding, this means you basically have to pay some factor that looks like alpha over the spectral norm of A eventually. So this is maybe not so easy to see in general, but it's certainly true in this particular case that I've given. And so this leads to a lot of nice ideas, right? Like if it's possible to do this encoding into vectors, then maybe we can do some interesting things with this, like in terms of like solving machine learning problems, because the way that these like block encodings operate on the quantum states sort of is just naturally like a linear algebraic type thing. This is not exactly the same with like probabilities. They sort of, because they all have to be non-negative, and they sort of behave in a different way. You can't exactly do the same things. Any questions so far?
Yeah, sorry, I had a quick question. If I want to chain together a bunch of these matrix multiplications, is it the case that my probability of acceptance decays exponentially because I have to get lucky in post-selection a whole bunch of times? Is there some trick to avoid that, or some way we can prevent that or something? So
right.
if I want to do like A squared or A cubed or something, do I have to get probability P cubed or something?
This is a great question. You can do a trick. But I'm not going to discuss the trick. I'm just going to say that you can do it.
Okay, but it gives you constant probability or something.
It gives you something. Yeah, so it gives you something that basically scales as like the degree.
Degree of
the like. So what you described is like to implement maybe like A cubed. So that's like, but you can generalize it to sort of any polynomial.
I got it. So it's the degree of the power that you're raising A to or something. Okay, great. Thank you.
Yeah. Yeah, I'm not going to get into the details of that, but
sure, but it exists somehow. So that's...
Yeah. It involves like yeah, you just have to do the multiplications in the right way.
Okay, great.
Yeah, I would recommend looking at like a talk of this paper for more details. Okay. But in any case, it's a good question. Basically, it's leading exactly into my next slide. where basically we can generalize all these notions that I discussed before. In this way, we can basically chain block encodings together to get block encodings of more sophisticated expressions. So for example, if we have an alpha I block encoding of AI for a bunch of i's, then we can get another block encoding of their linear combination. And the block encoding changes like by this amount. And similarly for the product, you can get a block encoding of the product of a bunch of matrices that you have a block encoding of. And finally, this is what I was alluding to before. If you have a block encoding of a matrix A, then you can get a block encoding of basically a polynomial of A over alpha, where P is some bounded low degree polynomial. So before, you would basically just want to put like P here is like, it's a little bit subtle because if you have to scale down by alpha, that means you sort of have to play with your polynomial to get it to behave in this whole interval. But in any case, I'm not going to show this one, but these two are fairly easy to see. So to encode this product, right, we have a bunch of UIs, which are our unitaries encoding each of the AIs. And if we want to encode the product, we consider the product, right, of the we consider the product of the unitaries. And as I guess some of you have already noticed, that you can just chain these together, and it'll give you precisely the exact block encoding that you want. And as for linear combinations, basically what you do is you just want to do a linear combination of unitaries. And so what do? You add some. You consider some way of preparing a state corresponding to the probabilities. So like you encode each of the you encode each of the coefficients of your linear combination as like a quantum state. And then what you do is you sort of like you apply UI basically conditioned on your initial state being I or something like this. Here's the precise details. You can just basically see that it works. And if you can implement UI, then and you can implement P, right? Implementing P is not hard because P is size because you're only dealing with O of 1 size Hilbert space here. But if you can do that, then you can implement all of this. And so here's just the proof that this works. I'm not going to dwell on it. And one thing to notice is that these two are indeed the natural ways you could think of upper bounding these linear combinations in this product, the spectral norm of these things. And well, 2 is indeed an upper bound on the spectral norm of a polynomial of A over alpha. This is, it's actually 1 would suffice, but there's a little bit of loss sometimes. And finally, one thing to note is that this low degree polynomial restriction is actually like, it's not actually usually used for polynomials. Usually what you use it for is for approximating Lipschitz functions. So if you're not aware, so first of all, some notation. I'm going to say f is like a scalar function is L Lipschitz if basically its first derivative is bounded by L. And this is just a notion that doesn't need a derivative. And if I have a function f in a matrix A, I let f of A denote applying f to the all of the eigenvalues of A. So here I'm using the fact that you can like the eigen decomposition of A here. And so something to note here is that f of a, like if you have a polynomial, p of a with this matrix function definition is the same as p of a if you just plugged a into your, if you plugged a into the polynomial directly. So you can just, this follows from the fact that, this follows from the eigendecomposition existing. And what I was going to discuss earlier is that basically, if you have an L Lipschitz function, then you can, then there's some polynomial that's like still pretty low degree that is able to approximate it everywhere in -1, 1. So this is like approximation theory. I just pulled any one of a variety of statements that you could say here. But what you do in practice, or I guess not in practice, but in these papers, is you want to find f of a. You want to find f of a for some Lipschitz function, and then basically you approximate it by some p of a, and then this is what you apply. This is the thing that you implement. Okay. So are there any questions about what I just said?
Perhaps not at the moment.
Okay, I can move on if there are no questions. Okay, so now that I've discussed sort of what you can do with block encodings, we'll discuss how you actually get block encodings in your quantum computer. So because block encodings are such like a powerful notion, there are actually relatively few ways of implementing such block encodings for like a generic A. One proposal to get block encodings is this thing called quantum random access memory, or QRAM. And the idea is that basically, if you give me some A, I construct this data structure. What it is, it has all of the entries. So this is the example for a 2x4 matrix. So I consider like I have all the entries here as the leaves of my tree, like my data structure. And then I consider like all the magnitudes, I guess the square, the magnitudes, square magnitudes. And then I just build this tree where you take each node above to be the sum of the two nodes below. And the idea with QRAM is that somehow there's some quantum hardware that's able to basically give you all of the data on a particular level in superposition. So you can see how this would scale quite poorly near the end. But the idea is that basically classical RAM, with classical RAM, you sort of need to have a lot of parallelization, and maybe here you could use a lot of parallelization to make this effectively work. But if you do this, you have a Frobenius norm size block encoding. So note that this is like much larger than the spectral norm in some cases. So this could be like a factor of square root n worse. And another way to get this is if you are able to prepare some like purification of a density matrix, and then you have a block encoding that's like trace of A size. So here, so you need to assume that A is PSD. And finally, one way to find a block encoding for A is if A is sparse. So this means like at most S entries, at most S non-zero entries in each row and column. And the entries are efficiently computable and bounded. So like it's possible to query in superposition for which entries are non-zero and what the values of those entries are. And then in that case, you have a block encoding of size S. So keep in mind the fact that these factors here. Something to realize is that if S is like constant size, this is actually not much worse than the spectral norm. But these two, the Frobenius norm and the trace, could be like, dimension factors larger. And this is an issue because all of our previous machinery could work for like polylog size time. We were only working with like the representation of size log n. So this might prove to be an issue. Right. So this is exactly what I mentioned. So this alpha block encoding means that you have to pay this factor of alpha over the spectral norm of A eventually. And these limitations are not going to be good for us in the long run. But this is just foreshadowing. So any questions about that? I'm going to dive into some applications of QSVT.
Sorry, one quick question. This is a cost coming from the block encoding. Is the sort of circuit depth required to run these unitary circuits that you're block encoded into buried here somewhere, or is that sort of an additional cost?
That's an additional cost.
Okay, great, thanks.
Yeah. It's never too big for any of the things that I mentioned though. So it's always like, yes, I believe that none of these things I've described actually have dependence on like instance dependent things. They're always like at most like polylog of dimension.
Okay, so the cost really is all on this alpha over A and not running the unitary that you're block encoded into. Okay, thank you.
Yeah. You could conceive of ways maybe to like there's certain other block encodings that like I guess you could make these in sort of weirder ways and have them be different, but it kind of is always about alpha in the end. That's the way I think about it, at least. Okay, thanks for the question. So now I'm going to discuss like what the issues are when you're applying this framework that I described to machine learning. So this is all taken out of like, or this is pretty similar to stuff that Scott Aronson was saying in like 2014, something like this. And a lot of it still applies here. So there's a lot of different applications that try to use quantum linear algebra to machine learning. They can all be rephrased as some sort of QSVT type thing. That's as follows, which is basically you have some sort of vectors and matrices that you have as input. And then somehow you encode these as block encodings, and then you encode the matrices as block encodings and encode the vectors as quantum states. Just somehow you get that. And then once you get that, you use QSVT to compute some algebraic expression of the input. So, if you give me a vector B and a matrix A, I can compute for you A inverse B. And this gives me the output as a quantum state. So I have to measure the output state and then maybe do this repeatedly to get some sort of like estimator for something that I want. And the hope is that we only ever dealt with a representation. So, and our representation is with, log n qubits instead of n real numbers, which is how they were like given to us. So maybe we can get this all done in polylog time, and this will be faster than classical algorithms for machine learning, and we'll be very happy with ourselves. So one particular example is this HHL algorithm, which is basically for matrix inversion. I'm rephrasing it here in terms of this QSVT framework. So as I alluded to before, we're considering some matrix A and a vector B. We're assuming that A is, for example, sparse to get our block encoding. So we're going to have, in this case, like an alpha block encoding for alpha equals S. And and to get these states as like the vectors as quantum states, we can also assume that it's in QRAM. And this is one way that we can prepare copies of B. Another way is to assume that B is sparse. This will also work. And once we do that, we can use QSVT to create some block encoding of P of A over alpha. So this is using the low degree polynomials thing that we discussed before. And here P is just some some polynomial that well approximates the inverse function. So so something to realize is that if f of x is equal to x inverse, then f of a is equal to a inverse. This is a definition. Yeah. Okay. And what p of x is going to do is obviously in like x inverse is sort of unbounded as you go up to 0, or I guess go to 0. So where you're approximating it is you're basically approximating it between like 1, and this would be like alpha times spectral norm of a inverse or a pseudo inverse. And then you're basically approximating like this curve here. This is x inverse. In any case, you just, the reason why you're doing it this way is because you're basically just saying, okay, my a has some minimum eigenvalue, and so I only need to approximate the inverse in this interval of minimum eigenvalue to maximum eigenvalue. And here the a plus is like pseudo inverse. This is just a straightforward generalization of a regular inverse. Okay, and so this has this degree if we do this approximation. And then we apply it to our vector corresponding to B. And then we do the post-selection that we discussed earlier to actually, so when we apply it, we need to like post-select to actually see it. And then once we get that, we maybe like, I don't know, like measure it in the computational basis, learn some information about it. And upon working out the details, this is how the complexity scales. So I've given you all the information you need to like about almost all the information you need to actually see that this is the case. But the important thing is that, okay, so the important thing is actually this factor of like this S is like the alpha, right? Which is like the how good our block encoding is. And then we also pay this like minimum eigenvalue type quantity. So if A gets poorly conditioned, then this blows up. And this factor is basically what you get from post-selecting. You just need to ensure that the vector that you get as an output state is like fairly large. Like if A inverse B is equal to 0, then you won't be able to do anything. And if it's close to 0, you also won't be able to see it ever. So you just need to account for this. You can, if that's confusing explanation, you can just ignore it. But yeah, so this is like the scaling. And as desired, right? I mean, there's some polylog that I sort of ignore here, but as we desired, there's no dependence on n. There's only dependence on this like one parameter, and you can assume that it's like O of 1 if you have sufficiently nice, like very, very nice A. But in theory, it could give an exponential speedup. Or at least it could give a polylog runtime. And okay, so that's like my example. So in this example, I've sort of there's been a couple of problems with what I discussed. The first thing is that we had to encode our matrix as a block encoding, and we had to encode our vector as a quantum state. I did, if the matrix is sparse, then I sort of can do this. And if I put the vector in QRAM, then I sort of can do this. But this is generally like not that great of a thing, especially if you want to eventually implement these things in practice. So so there was a slide from a Microsoft talk that was discussing how quantum computers are pretty poor at reading data. I was going to like copy the slide, but I did not want to get sued. So here's just a quote. And right? I mentioned that like, okay, so like maybe QRAM solves this problem, maybe sparsity assumptions solve this problem, but the sparsity assumptions are pretty restrictive. And then QRAM, well, it may or may not be able to be implemented eventually. But it also leads to like a poor quality block encoding. And so this is basically like encompasses the input problem that's often discussed in quantum machine learning. So this is like a thing that people talk about. There's also the issue of like output, right? Which is that like we have some output state that we want to like learn, right? We have the vector that has all the information that we need in a quantum state, and we want to actually get information from it. But the issue is that it's encoded in log n bits. So you can only ever get like log n bits of information out of your quantum state at a time. And you know, this is all like very highly random, and so you need to like really query a lot about it to get some information. And in the end, you might only be able to like convincingly learn like maybe 1 bit of information out of your output. Like, okay, like is this output state highly correlated with this other output state, or are they like, or are they not? And it's a little bit tough to see like how you could get a convincing speed up or get interesting information, because your Hilbert space is like super big, but you only want to, you know, you need to find out the particular 1 bits that you want to extract out of this output vector state. So it's like a bottleneck. Okay. And so now that I've sort of like covered the sort of issues that have been present in quantum machine learning algorithms, I'm going to discuss some recent work that I did with all these nice people. Are there any questions about what I talked about so far?
I had a question, actually. I was a little bit confused by exactly what role kind of QRAM plays. So you kind of mentioned that you don't really have to use QRAM. You can use a sparse, if you have a sparse vector, for example. And I was also confused. So is QRAM both being used to represent the matrix encoding as well as the vector, or just one?
So you could do, you could do both. You could do just the vector. In the application I described, I did it only for the vector. But you could do it for both. That makes it like, that basically changes the sparsity assumption to a low rank assumption.
I see.
And it's generally nicer. Like there are more applications, I guess. There are more papers and more applications for the case where it's low rank, just because I suppose like if you want to get an exponential speed up, it's easier to do it if you assume a low rank input. And there's more practical cases where your input data is indeed close to low rank.
Okay, thanks.
Yeah. Okay, any other questions? Or I'll keep going otherwise. Okay. So given all these issues that I've sort of laid out previously, so I've suppressed all of the quantum machine learning algorithms until now. So here's like a bunch of ones that sort of exist. And I've sort of roughly classified them based on like my feeling about how well they solve these like input and output type problems, and how contrived the resulting problem is that they solve. And so there are a lot of like different algorithms that sort of get these polylog runtimes and are claiming like, okay, like this seems to give an exponential speed up over what classical algorithms can do. So I didn't like put it here, but like factoring would be like yellow. You can't even see it. Like I just wrote factoring here. But like factoring would in this color encoding would be like yellow, because it doesn't have an input problem, right? It doesn't have an output problem, and the problem that it solves is like well studied and well and like believed to be hard for classical computers. None of the quantum machine learning algorithms that sort of exist now really quite get to the same quality. But something interesting was like, I guess like I had a recent line of work that sort of started to chip away at these exponential speedups. Basically, first of all, it started with this recommendation systems algorithm that proved that this recommendation systems paper, quantum recommendation systems paper of Karanidis and Prakash didn't give an exponential speedup. And then it sort of progressed to a bunch of other papers. Not all of these are like strictly like prove that some of them don't strictly prove like, oh, there's no exponential speedup in this case, but they just give classical algorithms that do basically the same thing with basically the same assumptions. Up to like polynomial slowdowns. There's no like exponential speedup. And so this sort of like raises the question of like, which quantum machine learning algorithms are still good? And something we basically notice is that all of these that I discussed that sort of have been quote unquote dequantized, these are all QRAM based QSVT, if you phrase it in the QSVT language. And these are all sparsity based QSVT. So there's sort of a natural question of whether you could generalize these techniques that were used to get these classical algorithms disproving exponential speedups for these quantum algorithms and generalize it to QRAM-based QSVT in general. And we're able to basically do that. So we define some notion that's an analog to the block encodings called sampling query access. Sampling and query access. And we have sampling and query access in the same settings where we have block encodings. And this sampling and query access has similar composition properties. And given sampling and query access to the output, we can recover the same kind of information as a block encoding. And so this framework basically captures the capabilities of QRAM-based QSVT. And this gives like strong evidence showing that QRAM-based QSVT doesn't really give exponential speedups. So this isn't like a proven statement. You would need to do some sort of structural induction on your like compositions or something, but we believe that is basically true. And just to give an example, these algorithms, just to give an example for like matrix inversion. Oh wait, this should be swapped. This is quantum and this is classical. Yeah. Okay. So just to give an example, here both A and B are in QRAM. In the previous example, A was a sparse, but we need everything to be from QRAM in order for our exponential speedup to, or for our algorithms to be polynomially like within the same like runtime. But just to give an example, this is the analog quantumly. We would just replace the S from before with a Frobenius number of A. And then the classical algorithm that we get is like this, which is not great. So well, you should think about like Frobenius norm times the spectral norm of A pseudo inverse as sort of like a piece. So this corresponds to like 28 factor slowdown. And the epsilon actually, there's like an exponential speedup there, but it doesn't matter because this just gets you the quantum state that you need to output. And if you actually wanted to estimate any quantity, estimate any like bit of output, you would need to measure like 1 over epsilon squared. You need to perform 1 over epsilon squared of your rounds of your algorithm in order to get like a good answer. So there's actually no speed up in the epsilon. But yeah, I'm just trying to say that like, if you're wondering whether these algorithms are, these classical algorithms are like actually good in practice, it's not, for like subtle reasons, they are like, the answer is, it seems like no, at least for like standard cases of these classical algorithms. The the major purpose is just to show that these quantum algorithms don't give exponential speedups. Is there a question?
Yeah, there's a question in the chat that I think is related. Do you think the bounds for the classical algorithms are tight? Do you think they potentially could be reduced to like a quadratic relationship, like with Grover search?
That's a good question. I think so. So this particular example of matrix inversion, there's been a couple follow-up papers. I think the number, the gap is down to like a factor of 6. I think maybe it might be 12. I mean, that's like a big difference, but I think it's 6. I'll show the reference for the paper with the best runtime here.
Okay, thanks.
Yeah, so it's sort of not like you sort of have run up against issues of like, for example, we don't know like matrix multiplication, like the complexity to perform like matrix multiplication. So you might like run into issues like that if you wanted to actually prove a quadratic relationship. But yeah, it's definitely something that I'm thinking about and people are thinking about. And it's a lot of interesting work trying to get these numbers down. Okay, so just to summarize what I said before, QSVT has this like fundamental like loop of you have block encodings, and then you get different block encodings via composition, and then you apply it to some vector to get your output. I guess it's not A, B, but just for some, you know, A that's like a, oh yeah, okay, it is for some A. Anyways, so there's a similar loop, which is you get sampling query access to a bunch of vectors or a bunch of matrices, and then you compose them however you want, and then you apply it to some B to get the output. Now, something to note is that like in reality, all of these algorithms are just like one shot. Like you get the block encodings, you do one transformation by a polynomial or by a function, and then you get the output. Because the complexities are lower that way. But in theory, you could do this like repeatedly. And I think it's nice to see that it's sort of the same, which is why I explained it in this way. Now, I'm going to just sort of like give the fundamental explanation of what the sampling and query access is, because I think like maybe it might be interesting. I'm not going to go into the details of like how these algorithms actually work. But okay, so this notion that is like our classical analog to the block encoding is, okay, we define it for both vectors and matrices. So if we have sampling and query access to a vector, this means that we are able to efficiently query entries of V. We can efficiently query the norm of V. And we can also efficiently produce samples corresponding to like this probability. So like this is basically somehow classically measuring the quantum state corresponding to V. So you can see how this sort of makes sense as a classical analog to a quantum state. Now for a matrix, we say we have sampling and query access to a matrix if we have sampling and query access to all of the rows, and we also have sampling and query access to the vector of row norms. So here A of I is the norm of A, the norm of the ith row of A. And so this is like the vector of row norms. So, so I'll give you one example. There's like I'll give you one simple example. So, if your V is just a bunch of say like 0 1s, then one way to get sampling query access to V is just you store S, which is the set of indices where Vi is equal to 1. And then you also store the size of S. So if our vector was 0 1 1 0, then we store like I guess we index starting from 1. Yeah, let's index starting from 1. So, all right, we would store 2 and 3, and we would also store 2. So you can see that we are able to query the entries because if we wanted to know what the entry 2 is, we can just see that it is in our set. And so the entry is 1. We're able to query for the norm. The norm is actually just the square root of the number of 1s. And then we're able to perform these measurements because the measurements are just a uniform sample from this set S. So this is just a simple example. That's like a specific instance of actually this QRAM data structure that I mentioned before, which is able to instantiate it more generally. So you can see that this actually satisfies everything you need for both, like for sample and query access to this matrix A. So there's this, all of the entries are here as you wish. All of the entries of A are here. And all of the norms are here. So this is the norm of the first row, norm of the second row, and norm of A. And you can produce samples just by starting from your root node. Let's say you want to sample from the first row of A. So you start from this root node. And then you recurse. So you sort of recurse down to a child proportional to the weight on that child. So you would go in this direction with probability proportional to A11 squared plus A12 squared. And by doing this recursively, you get a sample. But yeah, this is basically how you get sampling and query access. Yeah, are there any questions about this?
Yeah, can I ask a quick question? I guess I'm a little confused. Is the claim you're making that if you have sample and query access, then you can build a block encoded matrix using QRAM, or the converse of that, or neither of these things?
So I'm not discussing quantum anymore. So what I'm saying is like, this will give you, so the sampling and query access is an analog to block encoding. So it's like fully classical.
So I understood that, but I guess what I didn't understand is, given the ability to do this classically, does that automatically imply the existence of a block encoding that lets us do that as well, or no? There's no direct relation either way. Like if I hand you some matrix where you can do this sampling and query access, does that also automatically give me a way to block encode that matrix with low spectral norm or something, or vice versa, or neither of those directly analogous?
Yeah, so I've thought about this, and I believe the answer is neither.
Okay.
Yeah, you can sort of see this, that like block encodings are sort of like the way I defined block encodings was like pretty vague. Like any circuit could be a block encoding of like any sub matrix.
Take the upper left or something and call that the block encoding of that thing.
Yeah. So with that definition, it would be pretty hard for a classical algorithm to get something out of that. But yeah, but in basically in all of the cases where people have suggested ways to get block encodings for like machine learning tasks, there is like a way to get sampling and query access.
Okay.
Sorry, go ahead.
Go ahead.
I was just gonna say that like it's pretty intuitive that like it's pretty intuitive to see that this would be the right corresponding to like a state preparation oracle. It's a little bit harder to see that this is like actually a good analog to a block encoding as well.
And the other way is less interesting, but is it true that if I have sampling and query access, I can use that to build a block encoded matrix?
Also, I think no.
Okay.
So if you have sufficiently good control, like if you are able to say like, okay, if yeah, so basically like it's true that if you can, if your sampling and query access basically goes through anything like this, like if it can answer all of these questions, then you can build a block encoding. And
Through
this
a QRAM or
is,
something.
sorry?
Through a QRAM or something like.
Yes, this is like, I think this is like Grover Rudolph,
Okay.
something like a state preparation argument.
Uh-huh.
Yeah. But yeah, there is no like natural correlation, which is a little like a natural like reduction type thing you can do, which is a little frustrating. Because you want to say something stronger, but you're not able to, so you just say like, okay, this like it's conceivable that somehow like you make a block encoding strange enough that you don't have a sampling and query access analog, and all of like these exponential speedups like disproofs, these like barriers fall down. But, yeah.
I have a related question. Could you just construct this data structure, the classical one, for any matrix, or where does that go wrong? It sounds like it's only some class of matrices.
It works for any matrix.
So it is any matrix. Okay. So this basically you can always do the classical approach then for any of these problems. Okay.
Yeah. So if you give me an A, I can put it in this data structure pretty easily. I mean, it does take like linear time.
Okay, yeah, that's what I thought looking at it.
Okay, good questions. So if you wanted to generalize this, so actually I need to generalize this a little bit more in order to get the things that actually can compose. So I'm just going to quickly define these. So if I have a vector, I have sampling and query access with with respect to this parameter phi. If you have sampling and query access to some v tilde that sort of dominates v everywhere, so its magnitude is larger than v, and its 2 norm squared is equal to phi. So you have sampling and query access to some vector that dominates, and you also are able to query the entries of v. So one example of this would be like again, if we have some vector that's like 0, 1, then we have SQ sub n of v. If just immediately, we don't even need to store anything, because we can take v tilde, which is just the vector of all ones, right? So, and we have sample and query access to it. We can find the entries, they're all 1. We know the norm, it's square root n. And we can sample from it, which is just by picking an entry uniformly at random. And we can query entries of v. So, as long as we can query these entries of v, we're good. So you can see that this is sort of like, this is sort of how you would construct such things. And the same holds for the matrix case. You say I have sample and query access to A. If you have sample and query access to A tilde for some A tilde that dominates, and you can query the entries. And so you parameterize this by like phi. And notice that like here, before the alpha was an upper bound on the spectral norm, here phi is an upper bound on the Frobenius norm. And just something to note is that this is actually not that much. It looks like you can't learn and get any samples from V or anything, but you can sample from V and you can estimate the norm of V. So you can get something similar to sample and query access from V. You can sort of see like in this particular case, you can get a sample and query access. You can get a sample from V just by saying, okay, I'm going to sample an entry uniformly at random and then check whether its entry is 1. And this will give you a uniform sample from the 1 values of V eventually. Based on the ratio of phi, which is n, to the number of 1s, which is the norm of v squared. So this is just rejection sampling. It gets you what you want here. And yeah, so that was our notion. And I will just remark that you can get all of the sort of composition things that you want. So you can get linear combinations, you can get products. There are a couple changes here. So here we have, if you have sample and query access to A1 and A2, then we have sample and query access to M, where M only approximates A1 transpose, conjugate transpose A2. So this is like additive error, which is sort of fine for the quantum machine learning cases, but is sort of poor generally. And finally, if we have sampling query access to A, we have sampling query access to M for M sort of approximating the function A. Right, so it's sort of interesting to sort of compare how these values change and to sort of see that these actually do stay. These are actually upper bounds for the corresponding norms of the things that we have, the things that we have sampling query access for. But I'm running out of time, so I'll sort of discuss the major changes and then sort of finish. So the major differences here are that there's sort of additive errors throughout the process. We didn't see any of it, but there are large polynomial slowdowns if you want to actually implement it. And finally, it relies on the Frobenius norm rather than the spectrum norm. So as I discussed before. So sort of to explain in more detail, if we have sampling query access to A and B, and these are like perfect, so these are like the best that we could do, then we can get sampling query access to A dagger B. And in order to actually sample from this, right, we need to sort of like perform our post selection, our analog of post selection. And this would require this many queries. And notice that before here, this was alpha in our previous, in the block encoding case. In the block encoding case, this is like, this is something like this. But here, alpha has been replaced with the Frobenius norm. And this could be like significantly worse if alpha is good. But actually, if we are working with QRAM, this alpha, remember, was the Frobenius norm of A. So in fact, we are only polynomially worse. If this QSVT that we used before, if the QSVT we're comparing to is based on QRAM. So this is like fundamental, I guess, like this is the fundamental thing that makes our procedures only polynomially slower. It's basically just that like the QRAM block encodings are paying a factor of Frobenius norm of A. And this is large enough that we can actually get in there and get something that works only polynomially slower. Okay, so I think I'm running out of time, but I'm out of time. But here, this is the reference for the linear systems quantum, like a classical algorithm, corresponding classical algorithm. And there's still a bunch of algorithms that seem interesting for quantum machine learning purposes. But I'm not actually sure if any of these examples that I've described that are listed here are actually are like I'm listing them not necessarily because they're practical, but because they are interesting. So like interesting in terms of like they have seemingly super polynomial speedups, and maybe would be the next to analyze for either dequantization or proving that they're hard. But as for like practical things, it may be necessary to avoid QSVT entirely. I'm not sure. But yeah, thank you.
Thanks a lot for a wonderful talk. That was really interesting and kind of easy to follow, I think, for many parts. At least I enjoyed a lot of the linear algebra.
That's good.
Folks have questions for you.
So I have sort of a high-level question. Thanks for the nice talk. So QSVT is sort of the trick that's used for the best ground state preparation for quantum ground states. It's also being used here, but here it seems like the trick doesn't help above to get sort of exponential quantum speedup. And yet in ground state preparation, it seems that that's not necessarily the case. Do you have sort of any high-level understanding for why it works in ground state preparation, sort of breaks down in these machine learning contexts?
So I'm not familiar with this ground state preparation thing, but my guess is like the type of block encodings that they use are like much harder to simulate classically. Like this QRAM thing, and this also like this purification of density like this purified density matrixing that I mentioned earlier. These two approaches don't necessarily lead to good algorithms like via like they like have corresponding classical algorithms that you can figure out. But if you use this like sparsity approach, or like if you get your block encodings in some other way, like with the quantum circuit, then it's totally you get all of the power of quantum computing or quantum information.
Okay, great. Thanks.
Yeah, I have another question.
Mhm.
So I think the framework you have is very similar to like the randomized linear algebra setting, where if you use like a leverage score sampling, which is I think also a important sampling. So does it mean that if I have a algorithm, a linear algebra problem that I can efficiently solve via the leverage score sampling, then there's maybe another like corresponding quantum inspired algorithm that has a similar like efficient cost?
Yes. Yeah. So leverage score. So the sampling that we give is literally leverage score sampling, except you have some loss of a factor of like Frobenius norm squared over minimum singular value squared or something like this. And so you can do anything that you can do with randomized numerical linear algebra with leverage score sampling here. The main issue is that a lot of leverage score sampling algorithms, in fact, actually require you to run over your input. So the reason we don't use it here is because adapting leverage score sampling algorithms to this case is difficult because here we don't allow you to stream your input, like to at least look at your input. We only assume that you can get these important samples, and you have like polylog time in dimension. But in theory, you could just pay the whatever the number of non-zeros of A time and do all your stuff that you wanted to do. But it would be slower.
Okay. Yeah, thanks.
Mhm.
Any other questions? Okay, perhaps let's stop there. Thanks again, Ewin, for the talk and for answering questions.
Yeah, thanks for having me.